When we talk about ionic bonding, we're talking about the transfer of electrons from one atom to another, or one atom to several others, when we form actual compounds. So when we look at our periodic table, we realize that the A groups of elements are basically set up to form this pedestal, this set of steps that actually goes from one valence electron to two valence electrons to three valence electrons to 4 to 5 to 6 to 7 to 8. So if we draw this, and we're actually not going to draw an ascending set of staircases here, we're actually going to draw a podium. Because when we talk about the transfer of electrons, remember that that valence number, that magic number, is the maximum number of valence electrons, and that is 8 valence electrons. Okay, so when we start here at group 1, down here, this is group 1. And the Roman numeral is 1, or I, A. All right, they have one valence electron. So things like lithium and sodium and potassium, doesn't matter how many actual electrons are in them, in that last shell, they will always have that lone electron. And if that magic number is to get to a full valence or to get to 8, it's going to be very hard for these atoms to actually get to 8 because they're going to need to find 7 more. Okay, equally, group number 2 have 2 valence electrons. Group 13, all right, because we jump, have 3 valence electrons. Group 14 has 4 valence electrons. Now, all of these guys so far, with the exception of group 14, have less than half. So these elements right here, all of the atoms in these groups will predominantly be electron givers, which means that it's going to be easier for them to give up their electrons than it will be for them to find that larger number of missing electrons. If we look at group 1, they're missing 7 electrons. Group 2 is missing 6 electrons. Group 13 is missing 5 electrons. Now, group 14, we usually say that this is going to be a plus or minus 4, because depending on the situation, the atoms in this group might take 4 electrons, but they might also give away their 4 electrons. We actually tend to have these elements carry out a different type of behavior, and they don't actually, it's not a give and take with these kinds of elements, it's more of a sharing. So we're not going to actually talk about that type of bonding in this video. We're only going to be talking about the transfer. So when we look at this, if we keep going, we then get, and now this is where you're going to see the pedestal start to fall down. So if we go to, let's say, group 15, and then group 16, and then group 17, okay, we don't even talk about group 18 because they don't need any. So group 15, well, they are going to have 5 valence electrons, but they are only going to be missing 3. So these elements, 15, 16, and 17, end up being the takers. They end up taking electrons from the givers. So that means that group 16 is going to have 6 valence electrons, group 17 is going to have 7 valence electrons, and group 18 is going to have their 8 valence electrons. We don't really care about group 18 because they're inert. which means they're inactive. They don't want to form bonds. They will bond with themselves, and actually maybe even not. Now, when we look at this, we talked about our electron givers. Let's talk about these guys here as being our electron takers. Because even though you have 5 valence electrons, you're going to be missing, for that magic number of 8, you're going to be missing, okay, 3 electrons. You're going to need them to fill out that valence shell. In this case, you're going to need, for group 16, you're going to need 2 valence electrons. You're going to be missing those electrons. In group 17, you are going to need 1 valence electron because you're going to be missing 7. Now, if you notice this actual staircase, okay, or this podium, if we actually take, if we're looking at our 1-to-1 ratio that we discussed, elements in group 13 and in group 15, these guys are missing 3, and these guys, so these guys need 3, and have 3 to give, I should say. So they have 3, sorry. And these guys over here need 3. So that's that 1-to-1 ratio that we were talking about. So we're actually going to draw this out, and we're going to explain what actually happens in a diagram. So if I say that I want to talk about the example of lithium bonding with fluorine. Lithium is a group 1 element, okay? So lithium has an atomic number of 3. So we draw that, and now we've got our 2 electrons on the first orbit, and then they have that lone electron on that second orbit. So this is an atom of lithium. If we want to bond this to an atom of, let's say, fluorine, well, fluorine over here has an atomic number of 9, which means that we're going to draw our first orbit, and we're going to have these 2 electrons. We're going to draw our second orbit because it is in the second period, and we're going to add our 7 electrons. Now, we add 7 because 2 from the first orbit and 7 from the second orbit equals 9. And if we have 9 electrons, we will have 9 protons, and that is our atomic number. So, if we look at these 2 atoms, these atoms will form an ionic bond. They will form a transfer of electrons when they actually bond together. Fluorine over here is going to be our electron taker because fluorine only needs 1 electron to fill that outermost shell. Whereas you've got something like lithium. Lithium would actually need 7 more electrons, and that is so unlikely to happen that we say it will not happen. So what ends up happening here is the lithium atom sees that the fluorine only needs that 1 electron, and it comes over and it gives it to fluorine. And in so doing, it comes right next to it, and by giving it that electron, it causes it to form this bond. Okay, bonds are normally expressed with lines like this. So if we were drawing lithium bonding to fluorine, you know, that little bond means that there's a transfer of electrons there. It can also mean that there's a sharing of electrons, but ionic bonding only deals with transfers. So what ends up happening here is that we actually, in lithium, giving the actual electron over to fluorine, it eliminates this outer shell of lithiums. Okay, because that electron doesn't technically belong to lithium anymore. It's given it away. So lithium resorts back to its previous shell. And its previous shell is full because that maximum number of electrons on the first shell is 2. It cannot have more than 2 electrons on its first actual shell. All right, now, when these atoms are bound together because of this transfer, this entire compound, I should say, is completely neutral. It is very stable. And it is neutral because if we tally up the actual number of protons and electrons here, we've got 12 protons. And if we count our electrons, we will also have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. It also has 12 electrons. So this is a form of ionic bonding. Now this was a 1-to-1 ratio. When we talk about other atoms bonding ionically, it's not always going to be a 1-to-1 ratio. If we go back here and we look at something, let's say in group 2 here, okay, versus something in group 17, if we do that, so if we've got somebody like magnesium, which is 12 plus, so magnesium will sit there and it will have, okay, these rings. I'm only going to draw the outermost ring. And if we bond magnesium to, let's say, fluorine, again, we'll go with 9. We'll draw our rings, and we will actually include our outermost electron. So I'm just going to put an electron here and an electron here. Now, when we don't have that 1-to-1 ratio, okay, one of these actual electrons is going to end up going over and being given to fluorine. That is a given. However, this is not stable because of that lone electron over here. We cannot have a lone electron. So if we're looking at these two types of atoms bonding, if this guy still has one extra electron, if magnesium still has one extra electron to give away, then we're going to have to include an additional fluorine atom to take away that extra. Okay, I'm going to move this over a little bit to take away that extra electron. So the additional one would come over here at 9 plus, and we're going to draw our first orbit. And I'm even going to move that over a bit here. And we're then going to draw our second orbit. And that second orbit is going to have its 7 electrons. And it's going to take that additional electron. So this is where we have that non-1-to-1 ratio. Okay? The rule here in ionic bonding is it will always be a metal bound to a non-metal. And for the most part, the givers of electrons are going to be your metals and the takers are going to be your non-metals. All right? When we go to name these actual compounds, the metal always comes first. So in this case, we would have magnesium. And the non-metal comes second, and the non-metal's ending gets modified to IDE. So magnesium, instead of fluorine, we get fluoride, that IDE. And if we were to actually write out the chemical formula here, we would have 1 atom of Mg bound to 2 atoms of fluorine. So this is how we carry out ionic bonding, and this is how we demonstrate it by drawing atoms.